moving on with capillaries. By the way, we took care of the wasp. They had wasp spray back there, so we just sprayed it. Yeah, no problem. Capillaries down to one layer. They're just a TI. So that means they're only an endothelium. They do have a basement membrane. An endothelium with a basement membrane, and there's some other properties there. They're only 8 to 10 microns in diameter. They're only 1 millimeter in length. So they're not very long, they're not very wide, but they actually exist in great beds, capillary beds. Beds of capillaries, and it's the smallest blood vessels that provide the most cross-sectional area for blood to flow. Provide the most cross-sectional area. Now, area is length times width. We usually just say centimeters squared. Okay. For blood flow. That's what we say. When you have a wide expanse, when you have more area for a finite volume of fluid, the velocity of blood flow slows down in capillaries. As a result, the velocity of blood flow slows down, and that's usually provided in centimeters per second. Those are usually the units of velocity. Velocity is speed. The other thing I have there is rouleau. That word refers to the ability of RBCs to stack single file as they flow through individual capillaries. Because the diameter of the capillary is about the diameter of a blood vessel or a blood cell. So the blood cells can only go through one at a time, single file. RBCs can stack to file through capillaries, single file. Here's a picture of it. This is a muscle tissue, but you can see the capillaries just kind of filing through one at a time. Right there. Now the job of capillaries is to allow for exchange. The capillaries are an exchange medium. Now that exchange medium means that there's a degree of leakiness to allow things to diffuse and pass in and out. The vessel wall of capillaries are leaky. not really a scientific term, but what I mean by that is it can either be a range of leaky but not very much to very leaky. All right, so these are the different kinds of capillaries that we find in different parts of the body. For example, continuous capillaries, not so leaky. That variety, well, I say not so leaky, but what I really mean is the endothelium is more or less continuous with very few, if there are gaps, they're very narrow. Endothelium is continuous. Gaps between endothelial cells, gaps between endothelial cells, I just call them ECs for short, are small. So these allow the least exchange, and what you can exchange are maybe the smallest molecules in fluids like oxygen and glucose. You usually see these types of capillary beds with the continuous capillaries, examples of where you find skin and muscle. Because skin, well, that's a barrier of protection. So you don't want to let infections in. So if you get a cut, the capillaries there have less chance of allowing any bacterium in the body. Muscles, when they produce lactic acid from intense workouts, from intense exercise, you want to minimize the acidity of the blood. The middle category, the fenestrated, I say are just leaky. Usually how they're described is they're not continuous. You see gaps and clefts between ECs. And the fenestrated means the endothelial cells themselves, they got holes in them. And you can even see holes peppered in the surface of the cells. ECs have fenestrations. Holes. So they're porous. They allow things to pass more easily. Things like hormones, larger molecules can pass through these cells. So you usually see these like small intestines. Because you can absorb the nutrients from your food. Those are larger molecules. Or I said glands, like hormones, right? From the endocrine system. Because those hormones have to enter the bloodstream. Oh, kidney. I have an example of that. Because the kidney, they got to filter your blood, so fenestrated capillaries are good. The glomerular capillaries are fenestrated. Yeah, and then sinusoidal, those are the leakiest, very leaky. Very leaky. Well, you can just look at the illustration. The gaps and the clefts and the fenestrations are the largest. They actually allow whole cells to pass through in and out of the blood. Largest gaps, clefts, and fenestrations that allow whole cells to pass through the wall, through their vessel wall. And the best example are the sinusoidal capillaries in the bone marrow. Example. because the bone marrow produces the blood cells, and so the blood cells have to get into the bloodstream after they're made. Also, look at the basement membrane. It's a pretty solid layer there. As you proceed to this end of the spectrum, it's discontinuous basement membrane. So there's just varying degrees of leakiness. And I have more notes on capillary exchange, but I want to move on to the veins pretty soon. But here's a close-up picture of the gaps or the clefts that I'm talking about. A gap between cells allows things to pass through, or a hole, or a fenestration. A fenestration is a pore to allow things to pass through. Okay. And they even show an endoexocytosis process happening. That's also another possibility of the cell. We'll turn the lights off so you can see the histology view here. The black arrows are pointing to, well, the fenestrations are everywhere. I can't point to it. They're like, they literally cover this internal surface of a glomerular capillary, just to give you an idea of how extensive fenestrations are. The illustrators can't even do it justice. So fenestrations are holes in the cell, but you also have gaps and clefts between cells. Well, in our slide collection, what I did was I just took the parameters I always teach and I just looked for a blood vessel that fit. So I looked at this and I say, that looks like one layer to me. An endothelium with a basement membrane. And look at that. There's a blood cell, and it looks like it can just get through, right? So that fit the parameter, and that's a capillary, right? Okay, so it goes arteries, then capillaries, then veins. The veins are a collection and return system, and so for capillaries, in terms of relative makeup, not much, right? Just TI. There's no TM. There's no TA. All right, when you get to the venules, they're almost capillary-like. They show you a few, okay, identify cell. That would be a good quiz question. Smooth muscle cell, the TM. So when you get to venule, you're back to 2 layers. Let me clear the board. Venule, back to 2 layers. TI, barely got a TM, just a few smooth muscle cells. So these are right after the capillaries. They're collecting blood after a capillary exchange. Collect blood after. And I have more notes on capillary exchange and it's coming up. So we're coming back to capillaries, just to let you know. I just wanted to move on to veins before I get too sidetracked on capillaries. Collect blood. So after the venules, you'll have veins. Veins can either be described as small or large. So look at our microns here. We go from like the smallest from 9 to about 20. Remember, a hair is like 75, so this is still pretty microscopic. You jump to like 5 millimeters, right? You can see that easily with the naked eye. No microscope needed. And so veins as a category, they're either small or large, but they got you're back to all 3 tunics, okay? And what you see in the relative makeup is they have the highest proportion of fibrous collagenous tissue. They have the most pronounced TA. proportionally. The most tunica adventitia. Here's an example of, I just turned the lights on, I'm going to show more histology pictures. Let me see if I can point to the central venule there. I put the label right above that hole. But I just went to our slides and I'm like, okay, well, where do I know there's a venule? In the liver is arranged in these little lobules. So all the blood it receives from the intestine through the portal vein filters towards, I call it the shower drain, right in the middle there. It all flows towards the center. There's all these sinusoids of blood flow. And all of these cells that pack out the lobule are the hepatocytes that do the job of the liver. And it processes the blood. As soon as the blood gets to the central venule, it's on the way out. Okay. But that's an example of a venule. I mean, I don't barely see any vessel wall in there. But that's my example of one. I'm going to go back to this picture again. The large vein shown on the bottom there. And if you do a close-up, we can see the 3 layers. So what if I point there? I'm going for TI. What if I say, yeah, TM, well, all this from here to there. You can see the difference in tissue. That's all TA. You see the blackish, that's probably elastic tissue. You see that reddish versus the pinkish? The reddish is collagen. The pinkish is smooth muscle. Okay. Whenever you see blackish, that's probably an internal elastic lamina of that vessel. Okay, so you got all 3 vessels. I point to them there, okay, to make it easy for you. But now, okay, so we did the veins, the properties of the veins. You can see from this picture why we say proportionally the most, what? T, A. Yeah, very good. P. Sorry, so back to capillary exchange, circle back to that. Here's some more physiology I like to teach that's commonly taught with that. And let me define the parameters of capillary exchange. So when the blood flows to your capillaries and you exchange gases and metabolites with the tissues, everything's a fluid medium. Plasma is the fluid component of the blood inside the capillary. The interstitial fluid is outside the capillary. There's fluid inside the cells. So pretty much we have an exchange between these 2 fluid compartments in capillary exchange. And you depend on principles of diffusion and pressure to drive that exchange. So let me define the pressures in, well, I think you know what diffusion means already. Things flow from an area of higher concentration to a lower concentration. That's usually taught in 430. But I want to make sure these pressures are defined. Hydrostatic colloid, osmotic pressure. Hydrostatic, like I think of water pressure. Turn on the garden hose, and that pressure pushes the water out of your garden hose. You water your garden. That's an easy pressure for students to understand. So whenever I mention BP, blood pressure, I'm referring to the hydrostatic pressure. And we know that the heart can generate a hydrostatic pressure of something like 120 over 80. And this morning, we calculated how to present that as an average. What was the number? 93. Given 120 over 80. Of course, we could change those numbers and the mean arterial pressure would change. But it's always units of millimeters of mercury. This driving pressure that pushes blood from arteries to capillaries. Now, in capillaries, there's a big pressure drop. Maybe pressure drops to something like 35 millimeters of mercury, something like that. Well, it's definitely not 93. Because remember, as you flow through blood vessels, one become many. And as there's more room for blood to flow, blood flow slows down and pressure drops. Okay. So that's just a good old, it's like water pressure, pushes the blood forward. Now, the other force there, the colloid osmotic pressure, sometimes it's called blood colloid we like to throw these 4-word terms at you. If you ever see the acronym BCOP, that's what we're talking about. Blood is sometimes described as a colloid suspension. You ever heard that one? Blood is a colloid suspension. You got all the blood cells, like the red blood cells, and the plasma. And if you just took a tube of blood, you would let the blood cells would just settle to the bottom, but you don't want that. It's kind of like your oil and vinegar in your dressing, salad dressing. Like when the layers separate, before you pour it on your salad, don't you shake it up? Because you want it to be a colloid suspension that's homogeneous. Blood is like that. So that's where the term comes from. Osmotic pressure, like when you studied osmosis, I always tell my students water goes to where the most stuff is. So this is like a sucking pressure. You ever hear someone say, "Oh, I feel bloated"? It's that kind of pressure where you just retain fluids, like high sodium. When you have high blood pressure, doesn't your doctor tell you to go on a low sodium diet? It's like, why? Because this kind of pressure, all that sodium holds on to fluids. All of your red blood cells that are part of the colloid suspension holds on to fluids. So this pressure, it's a sucking pressure. It draws fluids into the blood vessel. This one pushes fluids out. This one draws fluids in. So they oppose each other. So I'll just simply put draws fluids into the capillary. All right, so this one pushes. So that's what I have here. This net flow of fluid in or out. It's called filtration, absorption. Those are the words that are used. So push fluids out, call that filtration. It refers only to fluids. Only to fluids. Suck fluids into you, absorption. So the pressures are hydrostatic versus blood colloid osmotic pressure. Sometimes it's called oncotic pressure, alternative term, or oncotic pressure. So in addition to the fluids being exchanged, gases and nutrients, they just follow principles of diffusion, high to low or low to high. Okay. If the concentration of oxygen is lower outside, oxygen will just follow its concentration gradient. So this is the model of the capillary that's usually presented to students. I've noticed books are starting to drop it, but this is the classic med school physiology textbook. It's in every physiology textbook. And they show those two pressures on here. So let me point them out to you. Where it says the P cap, it's kind of in blue. That's this line going from here to here. That's the hydrostatic pressure. And what we see, it's changing as you go from one end of the capillary to the other. So the capillary is stuck between arteries on one end, you have gas exchange, and then veins on the other. So they call this end the venous end, and this end the capillary end. At some point, there's like something that's referred to as the midsection, where these pressures balance each other out. Okay, so let me write on the board everything I think you should note about 3 parts of this capillary. And before I erase it, they denote the colloid osmotic pressure as this little pi cap. So I'll write that before I erase it. I'm not sure why they use that, but we'll go with it. So what we have here is, I'll just write on the board, arterial end of the capillary. Some capillary midpoint, midsection, where the pressure forces balance each other out in the venous end. So what I want you to extract from this figure is look at the left side, and I'll just say the P cap is greater than pi cap, whole greater than less than day. Well, anyways, let's put numbers to it. 32, 25. I won't use the units, you know what they are, right? Millimeters of mercury. The confusing thing is that they put a negative sign. I don't think it's confusing, but it confuses students. That's to show students that the force is in an opposite direction. So if this pressure forces fluids out, this pressure allows fluids to be drawn in. But which force is greater? This one. By how much? 7. So on this end, you have net fluids out. Net filtration. Now, do you see the white arrows on the bottom there? That's supposed to illustrate this net flow out, okay, right? This net filtration right there. Turns out, at some point right around here, the forces are equal. And so there's no net fluid exchange, no net fluids out or in. So it's like 25, 25. No net fluids in or out, because the forces are equal. Now, the pressure tends to drop to about 15 over here, so then the pi cap becomes less than, the P cap becomes less than the pi cap. It's like 15, negative 25. So there's net absorption. That's kind of what I want you to see there. Like I say on the bottom, that's just the fluid exchange. The fluid exchange, the metabolite exchange, is dependent upon diffusion. So to recap, here's the figure from your book that they're starting to use, and the way they illustrate it is they show an actual artery on the arterial end. They don't show just one capillary, they show it as an entire bed. So arterial end, midsection, venous end. You see the little black arrows. Those are illustrating the filtration, and the midsection, the no net exchange, and then the reabsorption there. That's cool. And then, but for the metabolites, what you should know is that O2 and nutrients diffuse out, and CO2 and waste products diffuse in. O2 and nutrients. O2 and nutrients diffuse out. On this end, CO2 and waste. It's usually nitrogenous waste. That's what we say. Diffuse in. However, there's a net for the fluids, a net filtration of 2 liters a day. So not all that's filtrated out is absorbed, and so that's the job of the lymphatics, to pick up the excess, so prevent edema or swelling. Well, I wrote it on the board, but it was on the previous slide. Let me just show you Randy, real quick. Net flow out 2 liters a day. So that's what I'm referring to. And so that's why on this picture, they put a little lymphatic capillary there, because that excess that's pushed out will be picked up by the lymphatic capillary. Okay. And this slide shows what we noted earlier about the blood flow. As you flow through the vasculature, you increasingly have more surface area as you get to the smaller arterioles, and then the capillary beds provide the most cross-sectional area. And it correlates with the slowest amount of, the slowest velocity of blood flow. That allows time for the gas exchange and the fluid exchange and all the exchange. You don't want it to be too fast, so you have no time for exchange. That's why they change from red to blue there. You get the gas exchange. Okay. So that's capillary pressure. But I want to spend some time talking about the pressure that you would measure in a patient, the blood pressure. And so I call this blood pressure basics. Make sure you understand systemic arterial blood flow and blood pressure. So just to be clear, as I raised the board, we have all these different kinds of pressures we talked about. Pressure in the arteries, pressure in the capillaries, pressure in the veins. The most important pressure are the pressures in your systemic arteries. That's the one. That's the vital one you want to keep track of. The vital sign of life, okay? So that's the pressure I think of when I teach this lecture. That's the pressure that's keeping blood flowing to your capillaries of your whole body. Okay? That pressure generated by the left heart, what we study. Let me define these basic terms: blood flow, blood pressure, or resistance to blood flow. All right, so the first thing, mean arterial pressure, MAP, is maintained by controlling blood, the inflow, the outflow of systemic arteries. So inflow and outflow in this lecture refers to arteries, not the ventricles like in the cardiac cycle. So you have to distinguish between the two. So I use this picture to teach that concept. Here's the arteries. So inflow is when you get past the aortic valve. Outflow is when we get past the arterioles. So inflow and outflow is different from this lecture. It's the systemic arteries that are the centerpiece. Systemic arterial pressure. So look at that CVP. RBC is capacitance, and you got volume and pressure. Now, I already taught this. We're not going to use the equation, but I taught it conceptually, all right? I said arteries have a small capacitance. So that's a small number. You don't even pick a number, just a small number. All right, so what volume do they have, large or small? They carry a small volume. What pressures did we observe in the arteries? High pressures. When you divide a small number by a high number, what do you get? You get a small number. That's the whole CVP thing, okay? The volume is small, but the pressure is high. The capacitance is small. Right, that was before the break. You can go back and look at your notes. But let's do the same thing for not just arteries, but look how they draw the veins. Look how they draw it compared to the arteries. So is the volume a big or small number? Big number. What pressures did we observe in them? Small. So when you divide a big number by a small number, you get a big number. Okay, so that's the whole relationship that I taught before the break. But I want to focus on the whole inflow-outflow thing in the arteries. So let me throw a very basic term up here. Blood flow. If this were a physics class and we're talking about fluid flow, you would just put fluid flow. But our fluid is blood, so I'll put blood flow. And sometimes we symbolize flow with a capital F. Flow is the flow of a fluid past a fixed point per unit time. Let's make our fixed point the aortic valve. Aortic SL valve. Okay. What's stroke volume on average? 70 mils per beat. You know, let's say you beat about 75 beats per minute. Well, the textbook average I gave you was, remember that? I call that the cardiac output of the heart. That would represent our flow. The average cardiac output during rest. Volume per unit time, right? Our fixed point is the semilunar valve, right? So in this lecture, let's call that our inflow. Cardiac output is the inflow. What are you flowing into? The arteries. Okay, that's the whole thing there. The whole goal is to keep blood pressure up. So, but let's just talk about the flow first. It's established by the cardiac output. So that's why I put this here. Our flow is due to the cardiac output. And you know that cardiac output is a product of the heart rate times the stroke volume. Okay, so that's why I put that there. All right, now let me define pressure. Pressure is, well, our pressure from blood is the enclosed blood exerts a force on the vessel wall. Find all the tunics, but let's just say that you have some thickness of the vessel wall from there to there, and then the blood inside, it's pushing, it's exerting a force in the enclosed space that the blood vessel provides, that pressure. So there's three kinds of pressure that we define: hydrostatic transmural driving pressure, And they use this vessel in the leg at a certain angle, you know, and they just take a section of it and you kind of make a free body diagram out of it. And the thing about pressure that we like students to understand, pressure is always the pressure difference between 2 points. Always. A pressure difference between 2 points. Now it depends which 2 points you're talking about in this section of a blood vessel here. For example, let's do hydrostatic pressure first, since it's listed first. Delta H. It's at an angle, but certainly against gravity, that's what hydrostatic pressure is, the difference between this point and this point, because this is in the leg. So where's your heart? It's up here. So I mean, it's like if it's down there, it has to get up here, like if it's in a vein, you have to think about that. So, for example, if you have to pump blood to your head and you're standing up, where's your heart? It's here. So you have to get it up to here. So you have to overcome gravity. Hydrostatic pressure. The pressure against gravity. But that's all I usually say about it. I talk about the other two like way more. Transmural pressure. That's the pressure across the vessel wall. I can illustrate that one right here. Like, how about like, boop, right there, and boop, right there. Just those 2 points. The pressure difference across them. Okay. Pressure across vessel wall. On the diagram, they blow it up and they put pressure difference between R1, R2 for that pressure difference. Here's the vessel wall. We've got the 3 tunics in there. This is very important in 2 locations, in the carotid sinus and in the aortic arch. 3 points. Carotid sinus. That sinus is basically the left common carotid, right common carotid arteries. And the aortic arch. So why is this one more? Well, this is a pressure that your body can detect. Okay, your body can sense that the blood pressure is dropping. Can detect. There's a branch of cranial nerve 9 that basically, you know, sends fibers to the vessel wall. It's inside there. And if there's a change in pressure, if the blood pressure is dropping inside the tube, if you're like a little nerve fiber that lives in there, you can detect. Okay. You did this in lab. You just didn't know you're doing it. When the subject lied down and then they sat up, the pressure was still supposed to drop. The blood's supposed to like start going down. And then in the aortic arch, which is right around here, the baroreceptor that detects that is supposed to send a signal to accelerate the heart rate. Do you guys remember observing that? Maybe, maybe not. But anyways, I'll reteach it in lecture, okay? So, boom, did it, okay? That's an important one. You have to be able to detect, your body has to be able to detect blood pressure, because the nervous system cannot detect blood flow, but it can detect blood pressure. And it's doing it really close to the heart, right? So if there's a problem, pick it up. That's why that one's really important. Now this other one, along the central axis of a blood vessel, call this one the driving pressure from here to here. So by definition, it's down the central axis of a blood vessel, right down the middle. Well, the artery. That's what I want you to think about. The artery. What I want you to see is, imagine you got the vessel wall, but then you have the lumen, you have a point right down the middle. Just drive the blood right down. Okay. And the difference in points, whether it be, they say x1, x2, if you're going to have this driving pressure, x1 better be higher. Okay, x1 is higher than x2 is the thing. So maybe it's 90, maybe it's 40 here. And if that's the case, blood flows from an area of higher pressure to lower pressure, just like, you know, I've been saying all along. But this driving pressure is the pressure that will keep you alive. It's the blood pressure that keeps blood flowing to the capillaries. I'll say keeps blood flowing to capillaries. That's the pressure that keeps you alive. So when you measure someone's blood pressure in the clinic or the ICU, or whatever it is, if you measure a normal blood pressure, you're measuring blood pressure at one point in the brachial artery. And what you say is, okay, well, if blood pressure is normal here, that must be enough pressure to push blood to capillaries. And that's all you think when you think that. Okay? You're measuring one point, and you assume it's high enough to push blood to capillaries. So that's when blood pressure drops. That's not good. Blood pressure is a function of how much blood is in the arteries. So if pressure is dropping, what does that tell you, the doctor or nurse, about the volume of blood in the artery? If pressure is dropping, what's happening to the volume of the blood? For whatever reason, you don't know, and you better get somebody or do something. Could be blood loss. There's many kinds of shock, but anyways, that's why. Measuring blood pressure is a direct measure of the blood volume in the arteries at the time you measure the pressure. Okay. So that's the driving pressure. So that's kind of the important one there. That's what I talk about here. So blood flow between 2 points along a tube depends upon a change in pressure, a pressure gradient, not the absolute pressure. That's the key. We need a pressure gradient. Not absolute pressure. So look at my pressure gradient here, 90/40. What's the gradient? 50. Good, we have a pressure gradient, blood can flow. What if I change this to 90. Will blood flow? Well, no. Why? Because there's no differential. Okay. It's not that it's not the absolute pressure. There's 90. It's that, well, where are you going to? It has to be lower. So that's the idea behind the driving pressure. It depends on this delta P, not absolute P. Delta means change. You gotta have a pressure gradient now. So this is a simple example. I just put in some numbers there just to give you an idea. You assume all other things are equal in the A-B examples of tubes and fluid flow. Well, which has a greater flow rate, A or B? What do you think? Which has a steeper gradient? A does. What's the gradient? 80. What's the gradient here? 25. So even though that's a higher absolute number, the flow isn't greater. It's because it's, depends where you're going to. So the answer is vessel A there. And then so it's to answer my question here, what cardiovascular structure generates this blood pressure in systemic circulation? It's the left ventricle. Okay, that's providing the pressure. So if you have enough cardiac output, that'll sustain the blood pressure, 120/80. Okay, so that pretty much defines blood pressure. The other thing, I think I'll teach resistance and stop. This is pretty much the resistance to blood flowing here. So we talked about inflow, we talked about measuring blood pressure in here. The other important thing is the outlet valve here, the peripheral resistance, that controls the outflow. Now in this diagram, what are the smallest arteries called before the capillaries? Arterioles. So those are pretty much your resistance vessels. They're controlling the fluid flow out. I mean, if you just completely open those all the way up, it doesn't matter what your inflow is. All the blood is just going to leave the arteries to the capillaries and get stuck in the veins away from the vital organs. So it's very important that you have this peripheral resistance or resistance to blood flow. They control the outflow. Now, resistance more generally is anything that opposes blood flow. And it's symbolized by a capital R. Okay. Now the number one thing that opposes blood flow is friction. Friction of blood rubbing against the vessel wall. So friction is like probably number one. Okay, but I want to focus on these four determinants there. Blood viscosity. It's pretty constant. The parameters of your blood, I mean, it doesn't really change very much. Maybe after you eat a fatty meal, maybe the fat sticks to your blood vessels and you get sluggish blood flow and you get tired, but that's just transient. Okay. Usually the viscosity of blood is constant, so R is pretty constant. But if for whatever reason you were to increase the viscosity of the blood flow, you would increase the resistance to blood flow. That's generally the relationship we say. But normally it's pretty constant. So let's just move on. Blood vessel length. The general rule is if you have two blood vessels and one is longer, all other things being equal, the longer one provides more resistance simply because it's longer. So if you increase vessel length, increase resistance. But that's usually constant in adults, because when you stop growing, the vessels stop increasing in length. So in adults, again, pretty constant. Maybe if you put on massive amounts of weight and all of that added pounds, you have to make new blood vessels for that. That might increase resistance, but generally speaking, constant again. Turbulent blood flow. Turbulence. If you increase turbulence, you increase the resistance for blood to flow. In terms of the vasculature, if you develop a plaque inside the vessel wall, now that little plaque, you force, like when you force laminar fluid to like flow over a bump, it creates all these little eddies and swirls. Well, anyways, that turbulence increases the resistance for blood to flow. Of course, blood vessels branch. Where you have a branching, that inevitably will be a source of turbulence, because when it hits the fork in the road, it creates all those it disrupts the smooth laminar flow. But the general idea is, okay, so branch points, plaques, increased turbulence, increased resistance to blood flow. That's all I'll say about it. The one we talk about most is, in physiology, is the constriction of the blood vessel. So the thing that affects capital R the most is vasoconstriction of the arterioles, the vessel radius. Affects resistance, capital R, the most. In fact, what we say is, what you'll see in your book is resistance is inversely proportional to the radius. Now, radius is usually symbolized, remember your not chemistry, your geometry classes, lowercase r. So don't confuse uppercase R, overall resistance, to lowercase r, vessel radius. So here's the lumen, here's the vessel wall. So pretty much from the center there, right, that's radius. So if you alter that by constricting, that affects it the most. In fact, it does so inversely to the fourth power. That's usually how you see it expressed in textbooks. So it's the biggest factor. So it's like, take a small arterial. It has sympathetic innervation. Maybe those precapillary sphincters. That's a nerve ending. I drew in black. And say in a fight or flight response, you constrict at one point, you clamp down at one point. You dramatically, you decrease lowercase r, you increase capital R. Okay. So because think about this, this is a part of an entire circulatory system. So blood can flow through here, but blood, it kind of stops there. So then what happens to blood? It stays in the larger arteries. It's not getting out. So this is very common of a fight or flight response. And well, what you're doing is you're diverting blood to working muscles, so you can, like, you know, whether you're running away or you need increased strength, you're shunting blood to the working muscles, you're keeping blood flowing to the vital organs, that kind of a thing. I'll talk more about that. Okay, I want to stop here. And I know you have a online test to worry about. We'll pick it up here next time.